In this video, we'll be talking about the multiplication principle in tree diagrams. To give you an idea of what we're going to be using tree diagrams for, let's look at an example. Let's suppose that you have two different color socks, green and white. You are a proud UNT Eagle. You own three different colors of shoes, red, orange, and purple. I don't know what that makes you. How many distinct shoe socks arrangements can you make? One way to help you see what's going on with this is to draw this out with a tree diagram. You have green and white shoes. You have red, orange, and purple. Sorry, I believe I said green and white socks, red, orange, and purple shoes. So you could have green socks with red shoes, green socks with orange shoes, green socks with purple shoes, white, red, white, orange, and white, purple. And you should be able to see there are 6 distinct combinations you can have. And this is an example of using a tree diagram and what it looks like. Now, again, we started here with 2 possibilities for the number of socks and type of socks, and 3 for the number of shoes, and we ended up with 6 things total. Let's see what happens with example 2. With example 2, we're told a competitor in a triathlon must choose from 3 different swimsuits, 2 different bicycles, clearly Cervelo is better, and 4 running shoes. How many choices are there? Well, we could do the same thing here. Draw out the 3 swimsuits and the 2 bicycles and the 4 running shoes. And this would get really big really fast. So let's actually look at that problem more carefully and see if we can figure out a general principle that will allow us to answer questions like example 2. What we see here is that in the first operation we had 2 distinct choices. In the second operation we had 3 distinct choices. And we can think of this as a series of things. We have step 1 and then step 2, leading us to our overall set of choices. We said again, we can think of doing this by first choosing the socks and then choosing the shoes. When we have situations like this, you have that definition there on your sheet. When you have operation 1 followed by operation 2, and you have, make sure I'm doing this right, N1 ways of doing operation 1 and N2 ways of doing operation 2, you can just multiply those out, and that will tell you how many ways you can do that thing. For these problems, and this is important, for these problems, you really want to break these down and figuring out what is your first operation, what is your second operation, figure that out, then determine the number of ways you can do each part. We're going to see an example where this gets a little tricky in a second, but that's really how you want to break these down. In example 2, your 3 operations are choosing your swimsuit, choosing your bike, and choosing your shoes. Alright? You had how many choices for swimsuits? You had 3 choices. You had 2 choices for your bicycle. And you had 4 choices for your running shoes. So we're going to find the product of those things. 6 times 4 is 24, so there are 24 choices overall. If I had drawn out this entire tree diagram, I would have seen there were 24 choices overall as well. So the tree diagrams give us a visual representation for these, and we're going to use what are called probability trees in a minute that are a type of tree diagram, but they're certainly a good way to demonstrate why the multiplication principle is what it is. So let's look at another example of the multiplication principle. On a multiple choice exam, there are 12 questions. Each of the questions has 5 potential choices. Determine the total number of answer sheets that are possible if each question is answered exactly once. Right. There are a few different ways, answers that frequently are come up with on this problem. But let's go through and do this problem the correct way. Before that, please pause this video and try this problem yourself. And I think it'll help you to see exactly what it is that you need to see about the problem. Again, please pause the video now. And now you're back. Alright, so let's look at this. When we're reading through this question, we first need to break it down. We need to determine what are the operations we're looking at. Are there 2? Are there 5? Hopefully that's 12, or are there 12? Alright, I a lot of times see people do something like this on the problem. There's 5 answers, there's 12 questions, the answer is 60. That's not correct. We're going to be real careful about this. Sometimes people just list out 5 things. Also not correct. The operations, the thing that you're doing on the problem, is you're answering the question. You're answering each of the questions. You're answering each of the 12 questions. There are 5 answers to each of the 12 questions. Hopefully that's 12 of those. If I multiply that out, there should be 5 to the 12th, or some enormously big number. 2, 4, 4, 1, 4, 0, 6, 2, 5, comma, 244,140,625 possible different answer sheets. Random guess, it's not likely to do too hot there, but that's the number of possible answer sheets to a 12-question exam with 5 questions on each part, or 5 possible answers on each part. In example 4, we're told 2 marbles are drawn in succession out of a box containing 5 red and 3 white marbles. Let's construct a probability tree for this experiment. What a probability tree is going to look like, and there's 3 different ways to write this, but I like to do it like this. We're going to have different branches along this tree, and that's why it's called a tree diagram, because we call these branches, and it kind of looks like a tree as it grows and all. But the different branches represent the things that can happen. Here, on the first draw, that's 2x right on, first draw, I'm just going to say it, that's the first draw. You can get red, or you can get white. All right. With the probability tree, this is a little different than the other trees. We're actually going to write out the probability of those things happening. When I first draw with replacement, well, there's a total of 8 marbles. 5 of them are red. So the probability of getting a red on the first draw is 5/8. The probability of getting white on the first draw is 3/8. Well, then I come in and I do a second draw. Red, white, red, white. Is what can happen. Now, what I mean by with replacement is, well, you draw in, you draw the marble out of the box, you look at the marble, you go, it's red. You replace the marble, that is, you put it back, you mix them all up. There's still 8 marbles, you're not looking, you pick around, and you draw one out, and you look at what it is. If I put the marbles back, nothing's going to change about this. But with replacement, second set of branches will have the same probability as the first did. One thing to note on a probability tree is that these probabilities along any one branching, these have to add up to 1. 5/8 plus 3/8, these have to add up to 1. Along each branching, something would happen. After I draw the first white marble with the second white marble, something had to add up, and that is these probabilities must add up to 1. For B, we're making a probability tree without replacement. Again, first draw, what can happen here? Well, 5 of the 8 ways we can get red, 3 of the 8 ways we can get white. With the second draw, I can get red or white again, but I need to be a little more careful. Without replacement means, I pick up the marble, I look at it, ooh, it's red, and I keep it out. So now, there's only 7 marbles left when I get to this point. How many of them are still red? Well, I'm holding 1. There were 5 total. That means in the box there are still 4 of the 7 marbles that are red. 3 of the 7 are white. If I come down here in the without replacement probability tree diagram, initially 3 of the 8 are white. I drew out a white. It's white. I'm holding it. There are 5 of the 7 marbles that are red, and 2 of the 7 marbles that are white. You'll notice these are different in the without replacement probability tree. In example 5, we're told a certain medical diagnostic test is used to determine if people have pinkyitis. It's known that 1 in 1,300 Americans has the disease. The test correctly diagnoses the presence of pinkyitis 97% of the time, and it correctly diagnoses the absence of the disease 98% of the time. Let's draw a probability tree to represent the situation. Okay, first, what you want to note is that there are people in the population and they either have the disease or they don't. That is, they have the disease, I'm going to draw that as D plus, or they don't have the disease, that's D minus. And you want to be careful about these definitions and how you write things down. 1 in 1,300 people has the disease. That means 1,299 out of 1,300 do not. To get this number, I'm taking 1 minus 1 in 1300. These two numbers have to add up to 1 because those are the two possible things that can happen. With the second part of the tree, probability tree, you want to recognize that these branches mean something. I went this direction and now I'm going to continue on from here. Well, when I do that, I need to be careful about recognizing what this means. This is saying that I have the disease. Well, in reading through what the problem says, the test correctly diagnoses the presence of pancreatitis 97% of the time. Well, that means the test will say you're positive for the disease, or the test will say you're negative. It correctly diagnoses the presence. You have the disease, and it says you have the disease 97% of the time. Well, that means 3% of the time, when you don't have the disease, the test says you're negative. Coming down here, well, the same two things can happen. You don't have the disease. The test can say you have the disease, or the test can say that you don't. This is called a false positive. That is, it says you have the disease and you don't. This is a negative test when you don't have the disease. This is a true positive. This is a false negative. Alright, it says the test correctly diagnoses the absence of the disease 98% of the time. So here you don't have a disease, it's correct 98% of the time, with probability 0.98. So the test would say that you're positive 0.0, with probability 0.02.